Good morning and welcome to Spark Summit in San Francisco. Today we'll be doing exploratory data analysis on various Wikipedia datasets with Apache Spark. We'll use Spark 1.6. However, I'll be making certain comments about Spark 2.0 and how certain things might be changing in the coming year. To begin with, let's go ahead and really quickly review this document that I prepared. This document actually serves two purposes. The first purpose is that I've put some notes here, preliminary notes for you guys, where you can see that if you have any issues with login today, you can send an email to this address. There's Wi-Fi information. The labs for today, I made some last-minute changes basically to the lab, so I would recommend downloading this labs file. It's only 2 megabytes. The slides you can download if you want as well. These links should be available for about 90 days, I believe. This is our schedule for today. It's about 9:05 a.m. right now. We'll take our first break in about an hour and a half. And then we'll have 2 breaks in the afternoon. I want to say that these breaks, I'm not going to take them necessarily right on that exact same time marker. We'll kind of play it by ear and see where we are. When we get close to the end of a section, then we'll kind of take a break. So the timings are a little bit blurry there. And then we'll come back to these things in a minute. Actually, so there's some information here, but there's some other things I might use this document for. For example, what I'll do here is make a new section, live notes to share with students. And this is where I might put certain snippets of code and things like that that I might just kind of come up with on the fly during class. So keep this open, and this is probably the first tab you want to open in your Chrome or Firefox window. The second tab that you're going to want to open is the community edition of Databricks. So the URL for that can actually be found in this document right here. So go to that URL. You should already have a username and a password since you're here in person. For anybody who's going to be watching this on YouTube later on, the way you can get access to this lab environment is you can go to databricks.com and then you can go to try Databricks for free and then just sign up for Community Edition here. You can do that without entering a credit card. This wait list moves quite fast, so you should get access to it within days or maybe a week or 2 at most. Go ahead and sign up for Databricks Community Edition if you're online, and then you should be able to follow along with this lecture. Okay, then what we're going to do is we're going to log in to Databricks. So let me find my own login credentials. Yes. Just talk to one of the TAs in the back, and they'll get you a login. If you don't have a login, you can also just kind of raise your hand, and one of the TAs should be able to come up to you and get you a login credential. Everyone's password is the same, so maybe what I'll do is I'll show you how to change your password as soon as you log in. Yes. Yeah, I will. There you go. Okay, once you log in, if you want to change your password, you can click on this icon in the top right and then go to user settings, and you can change your password here if you would like to. Your Databricks Community Edition account for everyone in this classroom is going to be active for roughly 1 month after class. So you can keep using the same login for an entire month. After that, if you want to keep playing with this environment, then I would recommend signing up for Databricks Community Edition. And then I'll show you how you can import all your notebook files into your own Community Edition account. Okay, so you can change your password there. We're going to be using this notebook environment from Databricks for a lot of today's class, about 80 to 90% of it. So I want to make sure you're pretty familiar with the user interface here. How many people here have used something like Jupyter or Zeppelin, just a notebook environment in general? Okay, something like maybe 60% of the class. So I'll try to point out some of the perhaps differences in using Databricks versus some of the other notebook environments. The first thing I want to ask you guys all to do is let's kind of, on the left pane, let's just kind of drop down to this clusters button and click on that. Actually, I want to get one more read from everyone. How many people here have used the Databricks environment specifically? Okay, maybe 10% of the audience. Okay, so we're going to launch a Apache Spark 1.6 cluster first. So once you click on clusters, just click Create Cluster. Type in your name. I'm going to call my Samir Demo. And I'll go with the default of Spark 1.61 on Hadoop 1. Notice that you can launch a Spark 2.0 cluster, but I don't recommend doing that right now because this curriculum was designed for Spark 1.6. Most of it should work in 2.0, but it's untested at this point, so I don't recommend launching a 2.0 cluster. Stick with Spark 1.6 with Hadoop 1. Basically, just type in your cluster name. You can do whatever name you want. Hit Create Cluster. And this cluster is launching now, and it should just take about a minute to launch. Another thing I'm going to do is, notice here I have some privacy extensions. I'm going to disable these. So I'm going to disable like uBlock and Privacy Badger. Specifically, these can cause problems with Databricks Community Edition. So please go ahead and disable any extensions you have. You'll notice that the cluster I launched is in a pending state right now. This cluster is going to be using a 6 GB container. And as soon as it's done launching, I'll get a link to the Spark user interface here. While that's launching, though, let me show you something else that I think is really useful for today. If you go to Workspace and then go to Databricks Guide, I just want to point this out as a resource for after class. Databricks Guide is kind of like a manual to Spark and Databricks. I would say something like 85 to 90% of what is in here is specifically about Apache Spark. And then maybe something like 10% of what's in here is more unique to the Databricks implementation of Spark. So let me show you a few of the things in here. One of the things I like to show actually is under visualizations. Maybe you want to make a D3 visualization. So you can click on this and you can scroll down and see how you can embed HTML and JavaScript into your Databricks notebook. If you scroll all the way down, actually, you'll see a D3 visualization that is kind of interactive. So I'm not really sure what this means, but it looks kind of cool. And if you scroll further down, you can see there's things on like debugging, how to run C++ code. There's a lot of stuff on Spark ML, actually. So for example, if you want to do something with logistic regression, you can come into this notebook and you can check out like more details about that. Now, one thing you'll notice here is like you can't double click on these cells. Like you can't do anything with these cells. You can't run them. So the way you can make these notebooks come alive is you can click on the Import Notebook button up here. And if you click on Import Notebook, then I'm just going to decide to import that into my root. So I'm just going to go to the root here and click on Clone. And then you'll notice it dropped me into this notebook right away. And this notebook is now under the root. And now what I can do is I can actually double click on these cells and I can actually see that this is really a markdown cell. And now I can attach this to like my cluster and I can actually run these cells. All right, that's how you kind of use Databricks Guide. We won't mess around too much with this specific notebook, so I'm going to delete this one for now. And instead what I would like to ask you guys to do is the following. Go into your class notes, and then this DBC file, let's go ahead and download this so we can get the very latest copy of the labs for today. This is a tiny 2 MB file. So if you go here and then click Download File, I'm going to go ahead and download it here. It's actually already in my folder. So go ahead and download that like 2 MB file to your desktop. Right, I got it from this document here, this labs.dbc file, which stands for Databricks Databricks Cloud. Okay, now that I have that file on my desktop, this is what I'm going to do. And this is the same steps you would need to take if you want to import these labs into your own Databricks Community Edition. Simply click on the workspace here, and then don't choose Create, but choose Import instead. Okay, so just like, right-click here, choose Import. And then you're going to import from a file. So I'm going to just leave that on File and click this. And then there's my labs. Click Open. And it takes like a second for it to import. And then click Import again. And you'll notice that it just populated the real labs folder under the workspace, which is different than the labs folder. The labs folder is basically, yes? Yes. So the Google Doc URL is right here. I'll make this bigger if you can't see it. So there you go. Okay. So I've imported my labs here under Real Labs, and I'll go through what this is in for just a few minutes. I want to point out that if you go to this labs folder here, you can get access to all of the classes that are happening today in San Francisco here. There's a basics class, the essentials class notebooks, the data science class notebooks, and then there's also the Wikipedia notebooks. However, we're going to use Real Labs because it's just got some of the latest stuff that I want to show you guys. So under here, what I want to actually first show you is not go through these notebooks, but I would rather first show you how to just create an empty notebook in Databricks and do some really fundamental things to look at the user interface. So we'll leave that folder as is, and instead we'll do Create Notebook. And once again, I'm just right-clicking here, and I'm choosing Create, and I'm choosing Notebook. It's going to ask me to name my notebook, so I'll call it My First Notebook. And I'll choose a language of Scala, and I'll attach it to the only cluster I have running in my account. So I just changed the language to Scala here. And I'll choose Create. Yes? Mm-hmm. Just raise your hand and ask a TA to help you, and a TA can help you with how to do the import. Okay, so now that I'm in my notebook, I can just write code here, like Scala code, like 1+1. I'll make that a little bigger so you guys can see it. So that's my results. I can declare a variable in Scala, like 10. And the way I'm running this cell is I'm hitting Shift-Enter. So if I hit Shift-Enter, notice what's going to happen right now is it's going to run that cell that the cursor was in, and it's also moving the cursor to the next cell. I can also, another important keyboard trick you might want to know for today is Control-Enter. If I hit Control-Enter, see how it's executing the cell, but it's not moving the cursor? So in Windows, the keyboard shortcut for keeping the cursor in the same cell while you can execute it over and over again is Control-Enter. Then I can just like keep hitting Control-Enter and it keeps running that cell. This is a useful technique when we're using like Spark streaming and we want to update the graph without having to keep moving to the next cell. So that's Control-Enter, but if you want to know what the keyboard shortcut would be on Mac, then you can click on this keyboard icon here. And that shows you some of the keyboard shortcuts specific to your operating system. Okay, so I have two cells here. Maybe what I actually want to do is I want to make a new cell in between these two cells. So the way to do that is, see if I like hover here, I can click this plus button. It opens up a new cell if I hit the plus button that shows up here. And then I can like add some new code there if I want. I can also delete that cell that I just made by hitting the X button right here and confirm, and that deletes it. Okay? You can minimize cells like this and just kind of play around with some of the stuff. You can copy cells, cut cells, you can move cells up and down as well. I think you can search in notebooks by clicking on the search icon here. So for example, if I make a variable called elephant and set it equal to 2, then I think if I click search here and type in elephant, maybe that doesn't search inside notebooks. I thought that would. I think that just searches for the titles of notebooks. So yeah, I guess you can't really search inside. Okay, one more thing is I'm attached to my cluster right now. If I need to detach from the cluster, I can just click this button up here and I can choose detach.
Just Control F in the browser.
Oh yeah, you're right. You can just say Control F in the browser and search for something. But if you want to search for something across 20 notebooks, I don't know of an easy way to do that. Notice I'm detached right now, so I'm going to reattach now to my cluster. And if you have any questions for the TAs, just raise your hand, and the TA should help you. There's like 2 TAs, I believe, in the room. If nobody comes, just put your hand down and try again in 2 or 3 minutes. Right? They might just be helping someone. Okay, so I'm attached to my cluster. There's another really important thing I'm going to show you, which is once you're attached, then you can do this. You can right-click on Spark UI here and open this up in the new tab, the Spark user interface. And then notice what's going to open up here is basically the Spark user interface, and it won't show any jobs right now. It's not going to show any jobs because we haven't run any Spark-specific commands, Spark-specific jobs yet. So there's a few things you basically want open throughout the day. There's going to be like a handful of tabs you always want open. So the class notes, keep that open. Keep the notebook that you're working in open. And then keep your Spark user interface open as well. The Spark user interface is going to be expired if you restart your cluster. So I'm not going to do it right now, but I just wanted you to see that you can restart your cluster by doing this, clicking this button. Don't do it right now, but if you do that, it expires your Spark user interface. So once you do a restart, you have to kind of close out of this interface. And then after the restart happens, then you'll need to open the Spark user interface one more time. Okay, so this is one of the procedures we'll be doing throughout the day. Every time we use a new notebook, we'll do a restart to give us a clean environment, and we'll open up the user interface one more time. Yes?
There is an issue with clusters in the pending state. IT knows about it, and they're working on it to help resolve it. So clusters aren't always spitting out at the time of hour.
Right now, you mean?
Yeah.
Okay, so how many people here have a healthy cluster? Let's go ahead and go to clusters right now. If you have a green icon there, that means you have a healthy cluster. Actually, let's do this. If you don't have a green icon that's healthy, then raise your hand. Okay, how many people, keep your hand raised if it's in a pending state. Okay, so it's just in a pending state right now. Just hang tight. Hopefully that'll be up in just a few minutes. If it does not resolve within about 2 minutes, then here's a technique I recommend doing. If it doesn't resolve in 2 minutes, if you're healthy and you have a green circle, don't do what I'm about to show you. However, if you have a cluster in a pending state, also don't do anything. Just wait for 2 minutes. If it doesn't resolve in 2 minutes, you might want to attempt terminating your pending cluster. I'm not going to do it because I have a healthy cluster, but you might want to consider terminating your pending cluster in about 2 minutes, and then try creating a cluster again at that point in time. By clicking the X icon right here. Okay, so we're about to get into the fun stuff in just a minute. Let's do this. Let's go to Workspace, and then everybody should have the real labs imported now. And I want you to ignore these two for now. These 2 files I'll explain in a little bit. Actually, I'll explain the first one. The datasets mount is how you can get access to these datasets if you're running Databricks Community Edition in your own account. You don't need to do this right now because this has already been run for you. And the mount has already been established. So you don't need to bother running the datasets mount notebook. That's just there in case you need to run that notebook in your own private Databricks Community Edition. What I want to actually show you is the fact that there's 2 folders here. There's a README folder and a RUNME folder. The README folder is basically, in this one, all the cells have already been run. And let me just give you a quick example. For example, if I go to the 00 notebook and if I scroll down, there's only one cell in this notebook with code in it. And see this cell with code, it has already been run and I can already see the results. Okay, but that's not as fun. Usually you want to be able to like run the code live and then see the results appear after you run the cell. So for basically, the only reason you're going to want to be in the README version of the notebook right now is if you don't want to actually run any of the cells. You just want to kind of sit back and scroll through the notebooks and not run anything and just kind of like see all the results already there. However, for the majority of everyone here, like 95% of people, I recommend going to the RunMe version, because in the RunMe version, if I go to that same notebook, I'm just going to scroll down and you'll notice that that same cell, it's there, but the code has not, like the results are not showing up until you run that cell. Okay, so this is what everyone should do right now. Let's go ahead and check out this primer notebook, which is kind of like the introduction for what we're going to be doing today. So like I said, go to Workspace. You should have the updated version of the labs imported. Go to RunMe, and then go to the 00 book primer. And then the first thing we're going to do is we're going to attach that to our cluster. Even if your cluster is in a pending state, you should be able to attach it and then just hang tight for a minute or two while your cluster becomes in a running state. So I'm going to go ahead and attach. And then I don't have my Spark user interface open, but that's probably fine for now. I'll get to that in a bit. Okay, so let's set the stage for what we're going to do today. We're going to be analyzing various Wikipedia data sets. So let me give you an introduction to Wikipedia. This is basically the philosophy of Wikipedia, or the mission statement of Wikipedia. Imagine a world in which every single person on the planet is given free access to the sum of all human knowledge. That's a quote from Jimmy Wales, who's one of the co-founders of Wikipedia. And for anyone here who is new to Wikipedia, hopefully no one in IT, but if you're new to Wikipedia, here's some information about Wikipedia. It was created in 2001. There's about 38 million articles across 292 languages. And in just January 2016, there were about 74,000 active contributors to Wikipedia. That means 74,000 people did at least one edit to Wikipedia, either anonymously or with a logged-in account to Wikipedia. This makes Wikipedia the largest collaborative project in the history of mankind, the largest volunteer-based collaborative project in the history of mankind. All these languages of Wikipedia get about 500,000 edits per day. And what about the amount of traffic Wikipedia gets? Well, it's about 374 million unique visitors per month. And almost all of the data that the Wikipedia project collects is released under an open source license, a Creative Commons license, which is great for us because we can use it to today in class. This is the main page of Wikipedia, and this page is going to come up multiple times, so I'm going to actually just load it for you. So I'm going to go to like wikipedia.org, and then I see all the different language editions of Wikipedia, and I'm going to click on English here to get to the main page for English. So you see this right here, it says kind of main page. This is the English Wikipedia main page. And you can see it just showing me a random article that's featured today, and it's showing me some stuff going on in the news. So let's go back to the notebook here. So this is one of the pages in English Wikipedia. There are 5.1 million articles in English Wikipedia and about 800 new ones being created every day. English Wikipedia is a 54 gigabyte data set. So if you actually download it from the Wikimedia Foundation, you get this massive XML file. It's one XML file that contains about 54 gigabytes worth of data uncompressed. This is like the snapshot of English Wikipedia if you get it right now. English Wikipedia has about 31,000 active contributors per month, and it gets about 7.7 billion page views per month. Okay, if you print out English Wikipedia, the snapshot of current English Wikipedia, without images and without edits, it's about 2,200 volumes. And this gives you a sense of how big this is with a life-sized human with a bunch of bookshelves next to him with books on them. right? So this is not cheating. This is English Wikipedia without images and without the full edit history. Let's talk about that edit history for a second. So as you know, English Wikipedia and all of Wikipedia languages are built slowly, piecemeal, edit by edit. If you actually try to download all of English Wikipedia with all the edits that built up the current snapshot, then it would be about 13 terabytes uncompressed. It's comprised of about 802 million edits. About 100 edits are happening per minute to English Wikipedia. We are not going to really tackle this data set today, but if you're interested in looking at some of these more advanced and larger data sets, then I recommend going to Databricks.com, and if you go to training up here, then you can check out like our private corporate training classes and our public training classes. And in our training classes, we actually attack some of the more sophisticated data sets for Wikipedia. And we offer like a longer 3-day class on how to analyze these data sets. Today, we're going to look at like a sample of maybe what we cover in our larger corporate training classes. Okay, so our tool of choice today is going to be Apache Spark. It's a research project that came out of University of California, Berkeley's AMP Lab in 2009, Apache 2.0 license. We will be using Spark 1.6. Spark 2.0 is around the corner. It'll be released very, very soon. We're going to be using Scala today, and one of the main reasons we're using Scala is because almost all the source code in Spark, 600,000 lines of code comprise the source code of Spark, and 75% of that is Scala. So there's two big benefits for using Scala. One, you can use all of the latest APIs as they're being created and released. You can also start using experimental APIs in Scala. The other major reason Scala is pretty cool is because if you need to debug your application, then it's much easier to be able to see how your application is plugging into the Apache Spark source code if it's the same language. Spark is built by about 1,000 developers across 200 companies, and it's the most active project in data processing. Today, we are going to be looking at all the different higher level libraries in Spark: SQL, DataFrames, machine learning, streaming, and graph. And one thing I'm going to do is I really want to cover all of these engines today. So I'm going to just set like hard deadlines on when I'm going to move into these topics, whether I cover all of the end of, I have about 4 notebooks on SQL and DataFrames. I don't expect to cover all of that material today. I actually am planning on covering maybe 60% of the material that I have today. So let me give you a quick summary for our goals for today, actually, since I'm on this topic. Okay, goals for today really quickly. This is from the slide deck. Oops, hang on. Okay, this is from the slide deck. So our goal for today is going to be to learn just enough about Spark to build prototypes and proof of concepts with Spark. We're going to have like a fast-paced, high-level overview of all the major Spark components. I'm going to spend about 40% of today reviewing Spark SQL and DataFrames. I think that's really the foundation of how to get into sophisticated analysis with Spark. So we'll spend a decent amount of time doing SQL and debugging DataFrame queries when they don't run as expected. We will look at all the engines for Spark. I hope to have kind of a mix of beginner advanced topics, but this is kind of an intermediate level class, so I hope to move fast between all the beginner stuff. And like I said, I'm not planning on covering all slides and labs, which means I hope you leave today with a lot of ideas and code and data sets to play around with after class. Okay, so really quickly, the goal of Apache Spark is to be a unified engine across data sources. You can see down here the data sources, some of them that Spark supports. In workloads and environments. Workloads is basically what Spark is made of. Spark is a compute engine. It's not a database. And it's a compute engine that can read from almost any file system or database. It can run in almost every modern environment. Today, Spark is going to be running in Amazon EC2, and the majority of the data sets today that we're going to be looking at will be either CSV or Parquet, or sitting in Amazon S3. So notice here that in the workload section where we can see Spark, at the bottom layer is Spark Core. Right above Spark Core is the RDD API. The RDD API should not be used by end users in 2016. In 2016, the RDD API has kind of been delegated to be this internal API that other Spark developers use to build the higher level APIs, like the DataFrames, SQL, or datasets API build upon the RDD API. So you can think of the RDD API kind of like assembly code, writing assembly, and these higher level APIs are kind of like higher level languages, like maybe, the analogy would be like Python or SQL sits up here, or Scala. So you really want to use these higher level APIs. You'll notice that they have bindings to 4 languages, and you can access almost all these Spark libraries through these higher level APIs. Okay, let's keep moving quickly. Spark Cluster 101. This is basically what a Spark cluster is made of. It's made of Java virtual machines. There's 2 types of JVMs. There's a driver JVM that's kind of like the head of your cluster, and then there's a bunch of slave JVMs called executor JVMs. You can run as many executor JVMs as you want. Here we're running 4 executor JVMs, and you can see that each executor JVM has 2 slots. This is perhaps just how I configured my cluster. So basically what you do is you write the code, and then you send the code to the driver JVM, and the driver JVM then schedules that code to be run in tasks on executor JVMs. Here we can see that the driver has scheduled like 5 tasks to run on my 4 executors. So we'll revisit this architecture later today. But the unique thing about today is we're not going to use a distributed cluster today. In Databricks Community Edition, this is what you're actually running right now. Your notebook, if you attach to your notebook successfully to your cluster, your notebook is currently connected to an Amazon EC2 machine, and that EC2 machine is being shared between 10 students. One of the students has so you perhaps have a 6 GB container. Inside that 6 GB container is a single JVM. This JVM is a 3.7 GB JVM, and it's running both the driver and the executor code in the same JVM. So the classes for the driver and the executor code are instantiated in this single JVM. There are 3 slots in this JVM. That means that at most you can run 3 tasks simultaneously. If for some reason you need to run, let's say, 6 tasks, then you can still do that. You'll have to run 3 tasks, then 3 more in 2 phases of computation. Okay, so this is exactly what you're running right now. You have this 3.7 gig JVM, and it has 3 slots. This is important to keep in mind because we're going to do certain optimizations today based on this specific architecture. This is called a local mode cluster, by the way. It's used for prototyping and learning Spark. Okay, so today there are 3 types of notebooks that we're going to be looking at: data analyst, data engineer, and data scientist. The way you can know what kind of notebook we're in is, notice here these notebooks have in their title it says either DA, DE, or DS for data scientist. That's how you know what we're kind of doing at that point in time. As a data analyst, we're just going to be running some simple SQL and data frame queries to analyze data, making some simple visualizations. But as a data engineer, we will rewrite some of the code that the data analyst wrote to make it run faster. And as a data engineer, we're going to be doing performance tuning, debugging, and optimizations. And then finally, as a data scientist today, we're going to actually be focused on unsupervised machine learning today. Specifically today, we will do natural language processing. We'll run TF-IDF, k-means clustering, PageRank, and the shortest path algorithm today. So these are all unsupervised machine learning algorithms, and we'll get to that around 3:30 or 3 p.m. today. Okay, so the very first line of code we're going to run is this cell. So go ahead and just put your cursor in this cell and hit Command Enter or Shift Enter. So everyone should have your cluster running now. So we're just going to run this cell, and this cell is going to use the SQL context to read a Parquet file, and then it's going to just order the results by the requests column in descending order and show us 25 results. And this is going to show us something really interesting. This is going to show us websites are being, which articles are being viewed on Wikipedia right now as of the past hour. So in the last hour, I can see that the Muhammad Ali article has been viewed the most. In the past hour, it was viewed about 22,000 times. The main page was requested 770,000 times in the past hour. If you scroll down, you can actually see other things that are happening in the world right now, because this is what the population of the planet is viewing on Wikipedia, and you can see how many requests happen to each one of these things. I believe Ramadan, the Islamic tradition of fasting for the month, started in the last 24 hours. I believe Novak won the Grand Slam, so in tennis, that's what's going on. Today is June 6th, so that's popular for some reason. And the X-Men movie is popular right now. Let's look at the Muhammad Ali article a little bit more in depth. By the way, I do have something interesting to say. Since I've been teaching this class for the past 6 months, Donald Trump has always made it in the top 25. This is a big thing. He didn't make it today. Okay, so let's look at the... I usually do this demo with the Donald Trump article, but today we'll do it with the Muhammad Ali article. So I just copied that article name, and I just pasted it here. And I'm going to load it up. This was the article title. So now we are looking at a specific article in Wikipedia. And I'm going to just give you like a Wikipedia 101, how this website works, because we're going to be analyzing this data, and I want you to have a sense of how all of this, some of the more sophisticated parts of Wikipedia work. First thing, notice there's a locked icon here. This article, along with about 200 or 300 articles out of the 5 million in Wikipedia, are in a locked status. That means that if I go to view source, I can't edit this article. See, it says I don't have permission to edit this page because it's in a locked status, and only registered users who have done at least 10 edits and have been active for 4 days or have had an account for 4 days can edit this article. This happens on certain articles that are really popular or trending or controversial, like Scientology, because basically to prevent vandalism. So anonymous editors can't edit this article. If I scroll down here, though, notice this is the actual article text. This is the text that makes the article that we were looking at earlier. This is important to look at because this is the text we're going to be doing natural language processing on later this afternoon. We're going to make a bag of words out of this actual text and then do things like word count and some more sophisticated things like creating a search engine out of this. Okay? Okay, so the other thing is the talk page. You can go to the talk page, and in the talk page, this is a different namespace in Wikipedia. There's like 20 namespaces. Namespace 0 is the article namespace. Talk is a different namespace, and this is where people who are editing Wikipedia articles will basically debate and come to consensus about a topic before that topic gets added to the actual Wikipedia article. Okay, so this is just where like Wikipedians are talking to each other about maybe controversial things or about things that they need to sort out before they can add it as something authoritative in the actual article. Okay, and then finally you can also like go to article again, and then you can go to history to look at the full edit history of articles. What I'll do is I'm actually going to go to the Apache Spark article, and then we'll look at the history of that. So let's go ahead and type in Apache Spark in here. It's Apache_Spark. And now I'm at the Apache Spark article. This article is not in a locked status. So I can go to edit, and now it's going to say something different than before. Now it's saying you are not logged in. Your IP address will be publicly visible if you make any edits. However, if you log in or create an account, then your edit will be attributed to your username, and it won't really show up with your IP address. So now I can actually edit this article, but I'm not going to make that kind of edit. What I want to show you now is the view history section. If I go to view history and I scroll down, I can see the last edit on the Apache Spark article was made on June 6th. Before that, it was June 30th. And I can see that this edit was made anonymously with an IP address. These edits here were made by logged in users, so I see their username. As I scroll down, I see something interesting, actually. I see a bot showing up, ClueBot NG. ClueBot is one of the 200 bots that's consistently watching the edit streams on Wikipedia, and it's preventing and defending Wikipedia, it's preventing vandalism and defending Wikipedia against malicious edits. So you can see that this specific bot, he deleted some stuff. So you see -9, he deleted 9 bytes of data, and it's saying reverting possible vandalism by this guy. This IP address was the previous edit. And he edited the Spark streaming section. Let's take a look at what ClueBot did by just going here and clicking on PREV, previous. So I want to see what ClueBot did compared to the way the page looked like previously before he made an edit. So I'm just going to click on PREV. I can see how the page looked like before ClueBot did the edit on the left. On the right, I can see what he did. So let me scroll down. It looks like the controversial line happened here around line 70. That anonymous editor added gibberish to the Apache Spark streaming section. So ClueBot simply deleted that gibberish. So it looks like the machine learning in ClueBot made a correct assessment to delete that. Okay, so that's looking at edit history. Let's go back to article, and there's one last thing I'm going to show you. See this AmpLab link? This is a red link. This link, if I click on it, it takes me to an article that doesn't exist. That just means it's a placeholder. If you want to make a new article on AmpLab where Spark was created at UC Berkeley, then you can just kind of click on AmpLab and you can start creating this article by logging in, and then you can make an article. Okay, that's basically all the introduction I wanted to do. There's one last thing I want to do before we get into the actual material. Let's finish up this notebook. We're going to do a pre-class survey, and then we'll get into the real code. I want you to know that all the stuff for today is being released under a Creative Commons license. There's a few different permutations of the license, but the short point is that you cannot use the code commercially, but you can share it with your friends and colleagues, and you can edit the code and put it on GitHub. You can do what you want to do as long as you're not using this stuff commercially. Okay, so I work in the training department at Databricks. My name is Samir, and the one fact I would like to tell you about Databricks is that the engineering team at Databricks contributed 10 times more source code to Apache Spark than any organization last year in 2015. So I hope you learn a lot from this conference today, where a lot of Databricks engineers will be talking. Okay, so a few other housekeeping sections. I'm going to jump to the code really quick. The slide deck really quick. And oops, let me change this. Okay, so here's kind of what we're looking at for today. We'll take a break at 10:30. We'll have lunch at noon, breaks at 2 p.m. and 3:45 p.m. These are the different data sets we're going to be looking at with different parts of Apache, with different basically libraries of Apache Spark. So you'll notice there's a small data set like 255 megabytes. There's Clickstream, page counts, English Wikipedia is 54 gigabyte, and then we'll be looking at the live edit stream of the 6 languages in English Wikipedia as well. A little bit about me. I've been working with Apache Spark for about 2 years now. Before that, I taught classes on NoSQL. My background is basically in working with Hadoop and Cassandra and Couchbase and a bunch of NoSQL databases. Before that, I worked at, before joining Databricks, I worked at Hortonworks and Accenture's R&D department and Symantec a while back. Okay. So one of the next things I would like to ask everyone to do is to please do the pre-class survey. If you have already done this, then you're fine. You don't need to do this. But for people who have not done this, this is actually really important because I'm going to review the results of the pre-class survey in about 2 minutes, and then I'm going to like kind of cater the difficulty level of today's class based on what I see in the pre-class survey. So this is your way to have like a voice today to kind of like give me a signal for what engine of Spark you're most interested in, like maybe machine learning or streaming or just Spark SQL. And also this lets me know how much you've played around with Spark. And this is going to let me decide like how complicated into the inner workings of Spark I get today. So please just take like a minute to do this. Okay, I have 37 responses, so I'm going to continue now. If you haven't completed it, please take like 5 seconds to quickly skim through and hit submit. Sweet, we have 45 responses. Let's see what people said. Okay, which of the following Spark components are you mostly interested in using? Everyone's interested in Spark Core, streaming, and machine learning with less emphasis on Spark's graph library. How much experience do you have with different programming APIs? A lot of people are actually maybe at the beginner or medium level in Scala, which is perfectly fine. You don't need to be like a Scala expert to do this class. Just fundamentals in any programming language is all you need to know. A lot of Java knowledge here today, and a decent amount of Python knowledge. Not too many data scientists, it seems like, in the room, so very little R knowledge. Everybody seems to want the focus of today to be development, 87%, with a little bit of maybe like administration or architecture type stuff. This is what I really care about. How experienced are you with Spark? So it looks like some people are at level 1, like they kind of like maybe 20% who have like launched the Spark shell, done some basic stuff. And most people here are actually in like level 2 or level 3. So that's pretty good. How long have you been doing hands-on development work with Apache Spark? Oh, wow. So most people are in the 1 to 6 month period. OK, that's pretty good. And where are you in the life cycle? Currently building a proof of concept or in production is where the majority of the people in the class are. Experience with machine learning. Most people seem to just kind of like know the basics or nothing about machine learning. And responsibilities, it looks like the majority of people are going to be writing Spark applications or doing data science and machine learning and making visualizations and taking Spark apps to production. So that's pretty good. It's a very developer-heavy class. I'll skip through this section, but you can skim through it. I find this interesting because this kind of shows you what projects in the Apache ecosystem are being adopted by your peers. OK, so thanks for doing that. Let's go ahead and jump into the actual, the first code notebook. So we're going to go to run me, and then we're going to go to this 01 data analyst page counts notebook. This is a pretty simple notebook, so just bear with me. We'll try to fly through this really quickly so we can get to the more, kind of the more harder notebooks. Once you load this 01 data analyst page counts notebook, the first thing I would like you to do is click on detached and then just click on your cluster to attach your cluster. And then another thing you'll want to do is you'll want to open up the Spark user interface. So just kind of like open this up in a new tab. And there'll be like maybe 1 or 2 jobs that will have run there. OK, so attach to your cluster. And take a minute just to kind of skim through this so you can kind of see what we're going to be doing in this notebook. OK. There's not much technical depth in this notebook. This is just something we want to fly through quickly. And for the people who are more new to Spark, maybe you'll find this useful. OK, so this section is a Wikipedia-only section. Let me introduce the data set we're looking at here. We're going to be looking at the Wikipedia page counts data, which is an hourly data set released by the Wikimedia Foundation. This file has all projects from Wikipedia, Wikibooks, Wiktionary, Wikinews, and it basically has the amount of traffic each article in these projects is receiving. You can get the raw files by opening this link up in a new tab. And if you go to like 2016, June 2016, and then you just kind of scroll down to the last file here, this one. This is the June 6th file from like 2 p.m., I guess, 1400. It's a 100 megabyte .gz file. This is actually the file that we're going to be operating on in this section, or rather a derived modified version of that file. So there's a new file that's being dumped there every hour. And what's inside this file is basically 4 columns. The first column gives you the project name. EN means English Wikipedia. FR means French Wikipedia. And then anytime there's a period, it means it's a project in the Wikimedia Foundation. Like en.d means Wiktionary, that's a dictionary. .b means books. So anytime it's en and then a period and then something else, it means it's one of the sub-projects. If for English Wikipedia, you can see that the second column is the page title, like main page or Apache Spark. Third column is the number of requests that we received that hour, and then total size of the content returned. So in the background at Databricks, we have a job running that is downloading the latest file, uncompressing the GZ file, and then it's doing a filter to keep just the English projects. So it's getting rid of like anything in French or Spanish, but it's keeping all the English projects. So en, en.b, en.d, all of that remains. And then we convert the resulting data to Parquet and write the data to S3. Okay, so we are operating on a derived version of that file. That S3 folder is right here. So let's run Control-Enter or Shift-Enter here. This is where the kind of like the derived hourly file shows up. And notice that this is a Parquet file that has 3 parts, which is ideal because we're going to be using a local mode cluster with 3 slots. So we can run 3 tasks to read these 3 files in parallel. And I believe this entire data set is about 30 or 40 megabytes. Okay, this is the Apache Spark section. So let's run this cell to actually make a data frame off that Parquet file. So this is how we make a data frame, SQL, read Parquet. We're going to name the data frame page counts, EN for English, all because it has all the English projects, and DF for data frame. I'm going to be naming the value or variable with DF or RDD or DStream. Basically, the type of the value will be at the end of the value name. This is just so it's easy for you to follow along. So let's run that cell. And now I should have a page counts English all data frame. Let's go ahead and look at the first 10 rows in that data frame. So just do a show 10 on that. Okay, that's interesting. So we can see the 4 columns, right? EN, we can see that this is the article that got 1 request in the past hour. Print schema with a capital S shows us the schema. So we can see that we have 2 strings, an integer for the request column. This request column is an integer, and that's the last column is long. They can all be null, so nullable is true. So I like to always do a count to get a sense of how long it will take to do a full scan of this Parquet file on disk. So let's run count. This is going to do 2 things. This is going to basically give me how many rows are in the file. So there's 2.6 million rows in this file, and it takes about 2.75 seconds to do a full scan of the 3 Parquet parts of the file. Okay, so doing a full scan on disk is under 3 seconds. That's pretty good. Let's go and start answering some questions. So how many different English Wikimedia projects saw traffic in the past hour? So we're going to take the data frame, select out the project column, the first column, run distinct on that, run show. This should tell us how many English projects saw any traffic at all. So there we go. We see English books, English dictionary. I think .n is English news. EN right down there is actually English Wikipedia. But how much traffic did each one of these English Wikimedia projects actually receive? So Yes, question?
The dollar sign and just putting in just
Yeah, this dollar sign is basically the way to refer to columns. If you don't do it, it will sometimes work, but the right technique is to actually this is just a way to refer to the column project. That's all this is. So notice here, we're doing something a little bit more sophisticated to answer this question. We're basically taking the data frame, running 4 transformations, and then finally calling an action. Show is the action, and these are transformations. Let's go and just run this, and I'll explain what this does in more detail in a bit. Okay, so now we should understand, in the past hour, we can see that the English Wikipedia project got a lot of traffic, about 7.9 million requests. And then the next highest is English Wikipedia Mobile Edition. And then we can see English Dictionary and books are the next most popular projects in the English ecosystem. So transformations and actions, you guys are already pretty familiar with Wikipedia, so you already know that there's 2 types of operations in Spark, transformations and actions. Transformations are lazy. They basically just take a data frame and give you a new data frame from that. So transformations just keep giving you new data frames, and then finally actions show you results. There's one thing I want to kind of mention here for people who are new to the Spark implementation of data frames. Maybe you're familiar with data frames because you used it in R or Python pandas. How many people here have used R data frames or Python pandas data frames? Okay, for those people, the most important thing you might need to know about the Spark implementation of data frames is that transformations here are lazy. That basically means that if you take a data frame and let's do a transformation on it. So let me just kind of like copy this, all these transformations here, and I'm going to open up a new cell, and I'm going to do this, and I'm going to hit Control-Enter. Notice this came back in 1/10 of a second. Transformations are lazy, and they don't actually run any code. Transformations wait until an action gets called. So if I add an action here now, and I do something like, let me just copy this action here, like show. If I run an action like show here, now this action is going to trigger these lazy transformations to run. This is really unique. The reason I'm pointing this out is because if you use data frames in R or in pandas in Python, as soon as you take a data frame and call a transformation, it's going to actually run computation. Every time you call a transformation, it's actually running computation. In Spark, the transformations are lazy, and they just kind of build up metadata until you get to the action. And then when you call that action, Spark's Catalyst Optimizer will look at all the different transformations and try to collapse them into the most efficient way, and then run all those transformations together. And we'll look at some of those things later today. But that's the most important thing you might want to know if you come from a different implementation of data frames. Okay. So here are some sample transformations which are lazy, and some actions that trigger the job to actually run. Okay, you can open up this API documentation in another tab if you're interested. And just keep this open for reference. We might come back to this later and look at some of this. But this is kind of like the Scala docs for data frames. And you can refer to this to look at more detail about the specific transformation or action you're going to be calling. And one more thing is tab completion. So if I open up a new cell here, notice I can type in just page and hit tab to autocomplete. Then I can do period, and I can hit tab again to see what are all of the methods I can call on my data frame. Okay, that's just to point out like a little trick you can use. Okay, what are the 25 most popular English articles in the past hour? Okay, to do this, we're going to first use a filter. We're going to take our original English all data frame, call a filter on it to keep only the English any rows that actually have English in the first column. So here in this filter, we're basically saying on the project column, triple equals is just a way to do a quality check against the column. So we're just saying anytime the column has a en in it, keep it. Now remember, this is a transformation. This is lazy. So this is going to come back in like just a few, like maybe a tenth of a second. And notice this didn't kick off a Spark job at all. I don't see any Spark job that I can expand here. So this just did some metadata addition. Okay, so now I have this modified data frame, or not a modified, this is a new data frame. Page counts en Wikipedia df, because we're keeping only the project en, which refers to Wikipedia. And then on that data frame, en Wikipedia data frame, we're going to do an order by requests column in descending order, show 25. And now notice the Spark job is actually running. Show is an action that's kicking off a Spark job, job number 11, which within it has a stage, 16. Now we can actually see the same results we saw in the first lab notebook. We can see Muhammad Ali received about 22,000 requests in the past hour. But notice something else. We're getting non-articles right now. We're getting like special, and we're seeing another special here. These specials are not actually Wikipedia articles. These are other namespaces in Wikipedia. So we actually want to do a filter to get rid of anything that is not an article, like the talk page or a user page. Let me explain what I mean here. Actually, one more thing I'll show you before I do this. Notice how we're doing a show 25 here. Instead of a show 25, we can do a limit 25, which gives us back a data frame. Let me show you that. If I do limit 25, notice that this returns a data frame. So I can take that data frame and then wrap it in the Databricks magic function of display, and then I basically just see the same results in HTML format. And I get basically an HTML table now. And maybe this is easier to scroll through or look at. So sometimes I'll be using display and I'll send it a data frame. Other times when I want to just look at the ASCII results, I'll just do I'll just run a show action. Okay. Let's talk about Wikipedia namespaces, because we're getting some non-article namespaces here. See, user is showing up here. For some reason, the user page for the Google API is very popular right now. So is Donald Trump's picture. Okay, so let's learn about Wikipedia namespaces really quickly. We want to keep only the article namespace, and we want to get rid of all these other namespaces in our analysis right now. So to explain, for example, look, this URL starts with the user : Jimbo Wales. This is Jimmy Wales' user page on Wikipedia. He can edit this, and this is like his username, Jimbo Wales, and he can put whatever he wants to here. It's his like own personal page. However, notice here now we're looking at Jimmy Wales. Now we're looking at wiki/Jimmy Wales. This is his encyclopedia article. He should not be editing this. This is the notable article, the encyclopedic article for Jimmy Wales. And then finally, by the way, this is the namespace 0. User is just a different namespace. And file is also a different namespace. File contains images. So this contains his picture. This is a different namespace. We want to get rid of all these namespaces. We want to look at just articles. So here's what we're going to do. We're going to take the page counts, English Wikipedia, articles only data frame, and then we're going to do just a bunch of filters on it to keep only, actually no, what we're doing here is we are basically getting rid of special articles or special namespace, file namespace, user namespace. So let's go ahead and run this, and then we'll get this resulting data frame right there. Okay, so let's go ahead and just run that, run all those filters. And then when we get the last data frame, we're going to finally do another order by the request column in descending order, limit 25. So this is pretty simple if you've been looking at data frames before, but the point here is to do a bit of a setup to do some of the more complicated things we're going to do in the afternoon. So I just want to kind of introduce you to this data set and namespaces right now. So here we go. Now we basically see the same results that we saw earlier today in the first notebook. Notice all of those filters did remove all the non-articles so far. Okay. Another question here. Question number 4, how many requests did the Apache Spark article receive in the past hour? So this is kind of interesting. What we're going to actually be doing today is we're going to be using Apache Spark to analyze Wikipedia, and a lot of times inside Wikipedia we'll be looking at the Apache Spark page. Okay, so right now see if you can figure this out. So basically start with this data frame right here that we kind of did some ETL on, this data frame page counts en Wikipedia articles only. Start with that, copy that into here, and then see if you can figure out what transformations you need to run, an action that you need to run to get this result. So basically the way we're going to work today is I'm going to give you a bunch of boilerplate code. You're just going to run it, Control-Enter, Shift-Enter. Then I'm going to give you some challenges to kind of reinforce and force you to actually write code from scratch. Now, if you want to get the answer to this, you can go to Workspace and you can just open up the Solutions notebook. The answer is in there, but try to see if you can figure this out on your own. Okay, so this is pretty simple, right? I'll do this with you. We're going to run a filter transformation. I want to do a filter on the article column. Can everybody in the back see this? Raise your hand if you cannot see what I'm typing. All right, thank you. So I want to do a filter on the article column, and I'll do the triple equality check. And I want to look for just the Apache Spark article. So that's my transformation, and then I'll just run a show to show me. Show by default shows 20 rows, but this filter should hone in on just one row. So only one row should be returned, not 20. Let me run that. So now what's happening is basically we're actually running the entire lineage of transformations that it takes to create this data frame. So we're not just doing a filter on the Parquet file. We're actually reading that Parquet file, then we're doing all the transformations that it takes to build up this data frame. Like we're doing those 17 filters, we're getting rid of all the other non-article spaces, and we can see that the request is 58. In the past hour on June 6th, the Apache Spark article received 58 requests. What about Apache Hadoop? So you can just kind of change that to Hadoop, and we can look for Hadoop. Hadoop received, let's see. It's usually a little bit higher, 153 in the past hour for Apache Hadoop. Which Apache project received the most requests this hour? So I want to take my data frame with just the articles. Let's see how many data frames are in there, by the way. If I just do a count on that, I mean how many rows are in there. It's going to be usually like about 2 million or so. Yeah, it's about 2 million. So out of those 2 million, maybe 20 of them are for Apache Spark projects. So what I want to do here is, on that data frame, I want to do a filter, but this time I'm going to use a regular expression to look for articles that start with Apache _. Now this might bring in other non-Apache related projects like Apache Helicopter. I'm not sure. Let's see what will happen. And then I'm going to do a request in descending order and then run show. So order by requests, and this is going to kick off a Spark job number 19. It looks like stage 25 is going to run. And there we go, that finished. And here are the results. Apache Spark received the most requests, 153, then Tomcat, and then there's Apache Spark with 58 requests. Okay, so you can see some of the other projects there. What percentage of the 5.1 million English articles were requested in the past hour? Show will just show me the top 2 rows in the data frame. And right, so what we want to do is actually run a count like we did before. And count is then going to show me, I think it was 1.9 million rows were requested, or 1.9 million articles, right? 1.9 million. Notice that took about 10 seconds to run. It took 10 seconds to run because of all the other things that are happening, like the filter and stuff that have to happen before this count happens. Okay, and then I can just take that count. Notice that gives me back a long data type. So I can take that long data type and put it in this equation. I do the 1.9 million divided by 5 million articles times 100. And that tells me what percentage of articles were requested in the past hour. About 37% of Wikipedia articles were requested at least once in the past hour, but that's a little bit cheating, right? I want to do actually something else live. What I want to do actually is before I do this count, what I would like to do is a filter. And you can just kind of watch what I'm doing here. I want to do a filter on the requests column, and I want to find times where the request was at least 3. I want to basically get rid of bot traffic like web scrapers from Google or Bing. I want to get rid of that kind of stuff and just look at articles that were requested at least 3 times in the past hour and count. And this should give me a much smaller number than 1.9 million. I'm basically trying to understand how much of Wikipedia is like freshly being requested. Now we're down to only about 300,000 articles out of 5 million. If I make requests 100, so now we're kind of looking at which articles are actually kind of popular in the past hour. This should be much less, maybe, let's see, maybe in the tens of thousands. Okay, way less, actually 3,500 or so, 3,400 articles were requested at least 100 times in the past hour. Okay, last thing here, how many total requests were there to English Wikipedia Desktop Edition in the past hour? So for this, what we're going to do is, notice this is our data frame we're going to work with. This is English Wikipedia Articles Only data frame, and this is like 5 articles in here. And we want to actually look at how many requests were there to English Wikipedia Desktop Edition. So that means in this column, we want to look for EN. So here's what we're going to do. We're going to import the Spark SQL functions, and then we will do a group by project and then run a sum on that. So we're going to group by the first column for EN. And there might be EN and ENW there. So let me show you how this works. Let's just run this first. So group by project, there we go. We're grouping by EN, and we have about 7.9 million requests in the past hour. I want to show you, by the way, that if you do a group by, notice this does not return a data frame. This returns a grouped data object, upon which we can call aggregator functions like sum. So since this is an advanced class, I want to dig a little bit deeper into this and kind of show you a little bit about how to think about these functions. Maybe you want to understand more about like what is really happening with sum. So this is just a demo. You can just kind of sit back and look at what I'm going to show you. I'm going to go to github.com and then open up the Apache Spark project. So I'll just type in Apache Spark up here. So this is just to give you some background about how you can learn more about what's going on behind the scenes. So here's the Apache Spark project on GitHub. Now what I'm going to do is there is a specific Scala class that I want to look at that contains the source code for the sum. So I'm going to hit T for like Tango, and then I can open up the functions.scala file. All right, so all I did is I hit T to do this file finder, and here's functions.scala. So these are the actual functions in the source code under Spark SQL that I just imported. So I can get access to it. See this? Functions. Here's the source code for that. Now this is useful sometimes to look at to understand like what's going on behind the scenes. Specifically, line number 612. By the way, look, there's a bunch of functions here, like average function. There's a bunch of other functions. Remember we had opened up here the data frame source code? Here are some of the aggregator functions as well. Anyway, let me actually show you the sum. That was like line 600, I believe. It's about 612. So here's like mean, minimum, and we're almost at 612. There it is. So those are the two implementations of sum in the source code. You can see that basically it's just calling the aggregator function for sum right there. Okay, so I'm not going to review the source code. My point here is just to show you how to get behind the scenes to see what's going on, to troubleshoot or diagnose some problems if you ever run into them. Okay. Yes? What's that? Okay, cool, thanks. Okay, so we understand how much traffic English Wikipedia received. How many total requests were there to English Wikipedia mobile edition in the past hour? So to do this, we're going to go to our original data frame, en all, before we did all the filters. So this is our original data frame. And then what we're going to do is filter for project en.mw for mobile. And then just do a count on that, and we'll get one result back. There's only one row that comes back. Let's do a show on that. And with mobile edition, Wikimedia project doesn't give us exact feedback for how much mobile traffic went to each page. And instead gives us this aggregated row that just tells us that mobile edition received this many requests. Okay, so we can see that desktop basically got a lot more requests than mobile in the past hour, almost twice as many. Okay, so this is 4.1 million, and desktop had received 7.9 million. Okay, so this is important numbers to keep in mind. About 8 million for last hour desktop requests, and about 4 million for past hour mobile requests. In the next lab, we're actually going to do a lot more analysis on mobile versus desktop traffic. Okay, so that's what we have so far. Let me see. We'll take a break in just a second. Let me see if there's any questions first. So we have about a few more minutes before we'll take a break. Are there any questions about anything I've covered so far? Just kind of raise your hand if you have any questions, just specific to the curriculum. Okay, just to set the stage for what we're going to do after break, let's go ahead and just get a few things set up. Let's open up this 02 Data Engineering notebook, DE for Data Engineering. And here's what we're going to do. First, close out of the Spark user interface if you have that open. Because we are going to, as soon as this loads, we're going to actually attach this notebook to our cluster, and then we're going to restart the cluster. Okay, so go ahead and attach this to your specific cluster, and then restart your cluster. This is going to expire the user interface. That's why I had you close the user interface, because that's not going to work after the restart. Okay, so I just basically am restarting my cluster. And notice right now I can't open up the UI, but as soon as this is restart, I'm just going to go ahead and preemptively open up the Spark user interface. In this notebook that we're going to look at after, yes? We're restarting to get rid of all of the old jobs in the UI so that you have a clean UI. Because we're going to be looking at the UI a lot in this next lab and learning a little bit about debugging and learning about what's going on behind the scenes. In this specific notebook, we're going to be looking at a 255 megabyte Pageviews file. You can actually download this file as well. I think in the next lab, there's a link to it. This lab is kind of unique because we're going to answer only one business question. We're going to basically answer this question: how many rows in the table in this file refer to mobile versus desktop? It's a really simple question, but we're going to linger on this question for a long time. We're going to actually linger on that question for about 15 or 20 minutes, and we're going to look at these specific technical things. We'll look at how, when you call an action, jobs and stages get kicked off. We'll learn about partitions in DataFrames and how that correlates to the number of tasks. We'll look at only these two transformations. We'll finally start looking at the Spark UI in depth. We'll look at data frame memory. We will start looking at Catalyst Optimizer, and we'll look at the specific setting in Spark. How many people, just by looking at this, know what this setting is or have changed it? So just raise of hands. Okay, this is probably one of the most important settings you should know of for Spark SQL. So we'll look at that as well. So okay, it looks like my cluster has restarted. Now I'm going to open up the Spark UI, and you should as well. So open up that Spark user interface. And you should have no job showing up here. See how this is empty down here? Nothing is showing up. That's what you should be seeing right now as well. Okay, and then you'll be in a good state to continue after lunch. After break. Okay, with that being said, it's about 10:28. Let's go and take a 15-minute break. So I'm going to open up a timer here, and I'm going to type in 15 minutes. So please try to be diligent with this and come back exactly in 15 minutes, because I'm going to continue right on the dot. So if you can be back in like 12, 13 minutes and get settled in, that'll be really great. We're going to resume exactly at 10:45 a.m. in 15 minutes. So feel free to grab some coffee, and I'll see you soon. All right, guys, let's go and resume. We've got an hour and 15 minutes before lunch. And before we jump into the actual notebook we were looking at before the break, there's just a couple of things I remembered that I would wanted to mention to you guys. One thing I wanted to mention is, as you know, we're not using these distributed clusters today. We're using this type of cluster. And one thing I want to mention is that when you use a local mode cluster like this, shuffles are free. Some operations in Spark need to do data transfer between multiple executors. And you'll see that later today. You'll see like a stage boundary and a shuffle happening. In a real cluster, when you do a shuffle, data has to move between different executors, and that can be costly. In Community Edition of Databricks, or a Spark local mode cluster, there's only one JVM. So basically, when a shuffle happens now, what's happening is this JVM is going to write a little tiny file, or a file basically, to the local SSD. So the first task that's running will just write a file to the local SSD. And then the next time a new stage opens up, and the next task that runs in that stage will just read that file from the local SSD. So there's no network transfer. I just wanted to point that out as one of the main differences between doing things in local mode Spark and a distributed Spark cluster. The other thing I wanted to point out is there was a question about what that triple equals trick was. When you do like a equality check on a column. Somebody was like, well, what is that triple equals thing? That's just looking to see if this project is equal to EN. But more specifically, if you come to the documentation here, and then if you just type in column, and you should just have this documentation open all the time. If you look at this column docs, here you can see more information about what this means to do the equality check. You can actually see that this is how you do an inequality check in Scala and in Java. And you can see other operations that can be done on columns, like greater than, or here's the equality check in Scala and Java. Okay, so this is column. And a lot of times we'll also be looking at data frame with a capital F. So in data frame, there's also like statistical functions. But we'll also be looking a lot at data frames. So just be comfortable with like skimming through this to understand a little bit more about what's going on behind the scenes. Okay, we are now going to jump into the notebook we left off at, the 03 Data Analyst Pageviews. So right now, you should have the Spark user interface open with no jobs, and your notebook 03 should be attached to your cluster. Oh, I'm sorry, not 03, 02. Thank you. Okay, 02, there we go, I'm attached. Okay, so a little bit about this data set. Wikipedia is the 7th most popular website measured by page views and unique visitors. Out of the top 10 global websites, Wikipedia is actually the only nonprofit in the list. And the Wikimedia Foundation has released 41 days of page view data starting March 16th, 2015 at midnight. From this day onward, for 41 days, there's 2 rows of data for every second. And this data is desktop requests and mobile requests. So there's 2 rows every second, 1 row for desktop, 1 row for mobile. So there's, I don't know how many millions of rows, we'll count in just a bit. So what we want to do first is get access to that data. So typically what we would do is perhaps we could upload that 255 megabyte file. So if you don't need to do this right now, this is just a demo, so just watch what I'm doing. If you go to the 03 notebook and you open up this new link here, you can actually download this file. You don't need to do this, but you can later if you want to. You can like download this Pageviews file and then you can uncompress it, and it's a 255 megabyte file. I got it by going to the 03 notebook and just clicking on that link. Don't bother doing that right now. Let me go back to the 02 notebook. Actually, let me show you one more thing. If you had downloaded that file and you want to upload it to Databricks Community Edition, you could do this, but don't do this right now. You could go to Tables, you could go to Create Table, you can choose File, or you could also actually choose S3 or JDBC if that's where your data is. I'm just showing you how after class you can get your data into this environment that you're learning how to use today. Say I have the file on my computer. So I'm just going to choose File. And then I actually happen to have a downsampled version of that 255 megabyte file. This is a 4 kilobyte sample of that file, just so the upload will be really fast. So I can upload that, and then I can click Preview Table, and then I can type in a sample name for this file. Maybe I'll type in PV sample for Pageviews sample. And you'll notice that it has already detected the column delimiter automatically. And one thing it didn't figure out is actually that this first column is actually a header. That's actually a header, so I'm going to click on first row as a header. And then this is not a string. This is int. So maybe I'll make those changes. This Spark can't read this timestamp column correctly. So you have to take this in as a string and then cast it as a timestamp, as you'll see how to do later in this lab. So for now, though, this is all you would do, and then click basically Create Table. If you do that, then this would make a file. I guess I'll do that here just to show it to you. And then see, now I can see a preview of my table. Now if I go to Tables, I can see my Pageview sample table. I can see that it has 3 columns, 2 strings and an integer, and I can see some sample data. Okay, I'm going to go and delete this table because nobody probably should have followed that, because we're not going to upload a 255 megabyte file to Databricks. That might take too long on the Wi-Fi. Instead, we're just going to sidestep that and read it directly from S3. So let me scroll down. I'm going to go past this uploading section. There's instructions on how you can do this, but I already showed it to you. We're going to pass this, and instead, we're going to jump into this section, and let's go ahead and run this cell with Control Enter. Okay, so now I'm getting this data frame called Pageviews loader, and it makes that data frame Pageviews loader, and then it registers a temp table called Pageviews by second. Just really quickly, this is basically using the Spark CSV library to read our CSV file on S3 located here. And it's saying that the delimiter is tab, to go ahead and infer the schema to figure out string versus integer, and it's saying header is true. Then you get a data frame. After that, you get that data frame, you're just registering a temp table so that you can refer to that data frame with this alias of the table name. After that, we're going to basically pick up now as if we had uploaded that file. So if you uploaded the file and you gave the table name Pageviews by second when you did the upload manually, or whether you read it like this and registered a temp table, regardless of how you did it, this is where we're going to pick up. Now we're going to basically read that table and give it a data frame name, Pageviews data frame. Okay, let me make that a little bigger as well and go full screen. Okay. Now I have an alias to my table. Pageviews DF is pointing to our data frame. Yes? They're actually the same thing. The reason I'm doing it this way is because if you had done the upload of the file, then this is kind of where you'd be picking off, and that's the main reason I'm picking it up here. Yeah. They're both the same thing, though. Okay, we have our Pageviews data frame. So there's certain things I like to always do when I make a new data frame. I want to show 5 records. One thing I'm noticing right away is the data is out of time sync. So the data should be March 16th midnight, 2 rows every second, but I'm not seeing the first row at midnight. It's 9:55 a.m., and then the next row is jumping to 10:39 a.m. So it looks like the data is out of order, so we'll have to fix that. And also notice that if I expand this, I can see a Spark job that is run. We're going to learn a lot more about Spark jobs in a bit, but here we can see that a Spark job ran with only one task. It basically ran job 13 with one stage, stage 13, which within it had only one task that ran. One task ran and it ran successfully, and it showed me these results. It only ran one task because it didn't need to look at all 3 of the files in the Parquet. Actually, no, this is not Parquet. This is a CSV file. For this CSV file, I basically just used one task to look at the beginning of the CSV file. This is going to look different in just a second, so just kind of let's just keep going, and you'll see something different in just a bit. Let's also print schema here. String, integer. Okay, that's fine, but as you know, we need to fix the timestamp column because that should be type timestamp, not string. So we'll cast that correctly later. Okay, let's do this next. On Pageviews data frame, let's convert the data frame to an RDD and then count how many partitions are there. This is a way to understand how many partitions are in the data frame itself. It says 4. So why 4? We never actually told it to give us a data frame with 4 partitions. So where did it pick this number 4 from? So let's learn about partitions and tasks to answer this question. So this is what our Pageviews data frame actually looks like. It has 4 partitions. These are dashed lines because the partitions are not in memory right now. This is just an idea that if you actually read the data frame from disk and do some operation on it, then it would actually load this data frame into memory. It has not been loaded into memory right now, which is why there's dashed lines right now. These 4 partitions contain about 25% of the data. The data itself is 255 megabytes on disk. So why 4? It uses 4 because of the input split. So we'll come to that in just a second, but just kind of hold that thought. Basically what Spark is doing is out of that 255 megabyte file, it uses one task to read 64 megabytes of that file. So it basically uses 4 tasks. The first 3 tasks read 64 megabytes each of that file, and the last task reads the remaining 58 megabytes of the file. So that's why it's using 4 tasks. So I'll show you that by going a little bit deeper into what's going on here. Let's run a count to do a full scan of the file, all 255 megabytes. And count is going to tell us how long it's taking to do a full scan of the file on disk, and it will tell us how many rows are in this file. So this is going to take, I think it's about 5 to 10 seconds. Let me expand this. And I can see that it's basically running job 14. The first stage is using 4 tasks. It's using 4 tasks. Each task is creating one of these partitions. So all 4 tasks are reading from the same underlying 255 megabyte file. They're just reading different parts of the file, different sections of the file. They're each reading about 25% of that file. And in just a bit, I'll explain why this stage 15 is being run with 1 task. However, I can minimize this, and I can notice that the count gives me back results of 7.2 million. That means that this file has 7.2 million records, and I can see that it actually is taking much longer than I thought. It's taking like 30 seconds to scan this file on disk. So before I do any sophisticated operations on it, I probably want to load this up into memory. Okay, so we already looked at this by expanding that. Let's go ahead and open up the Spark user interface. We should have already had that open in another tab. My count job, let me just scroll up. See my count job here? It ran job 14. You might want to check what specific number your count job ran, what job number it ran, because that's the job number we're going to look at right now. We're going to spend like a few minutes analyzing what just happened in the background. Okay, so let me refresh this jobs UI by clicking on jobs, and here is job number 14. Okay, notice I just basically found that by expanding, jobs here, and I see job 14 there, and this is job 14 now under my UI. I can see that this job ran for about 31 seconds, and it had 2 different stages, and across 2 stages it had 5 tasks total. Let me click on this link under description. And now I'm drilling deeper into job 14, which has 2 stages, stages 14 and 15. So once again, I can expand job 14 and I can see stage 14 and 15. Stage 14 had 4 tasks. So once again, I can come here and see that stage 14 has 4 tasks. And these 4 tasks together read an input of about 250 megabytes. And these 4 tasks emit 168 bytes. So they're basically reading together 250 megabytes, and then the 4 of them emit 168 bytes of data. That 168 bytes of data gets read by the next stage. The stage 15 is not doing any input read from like S3 or any database source. The stage 15 is just basically reading what the earlier stage handed off to it. Let's look a little bit more deeper at what's going on in stage 14, the first of the 2 stages that kicked off for this job. So we're going to click on this link for description. And then we're looking at the details of stage 14. Let's just like jump way down to the bottom to look at the 4 tasks. So here are the 4 tasks. I can see the task ID relative to this stage. I can also see the task ID relative to the life of the cluster. So ID 14, 18, 19, and 20. This is the ID that would be seen in the logs of the Spark job. So if you want to actually look at this in the logs, you'd be looking at these IDs. I can see that this first task ran for about 18 seconds. For 1 second of that time, approximately, it was in garbage collection. And it read 64 megabytes of data, that's the input size, and the number of records it read is about 1.8 million records, or 64 megabytes of data. The next task also ran for about 18 seconds, read 64 megs of data. Third task read 64 megs. The last task read 58 megabytes of data. And the last task only read 1.6 million records. This first task that ran for 18 seconds, it wrote out 42 bytes of data or one record. I can see that each one of these 4 tasks read this much data from S3 and basically wrote out only one record. So after this stage completed, 4 files were written to the local SSD. Each file was about 42 bytes and it contained only one record. Yes?
Do you know why the write time is not documented for task 0?
It was probably just really fast. That's why it's not documented. I'm not sure. It ran really fast for those 2 for some reason. Yeah. And we'll talk about what this 42 bytes is in just a bit. I have a diagram to explain this. But let's just notice that what's going on here is basically each task is reading 64 megabytes of the CSV file. Then it's actually doing an aggregation. And then based on the aggregation, it's realizing there's only 1.8 million records. That's the number that it's writing here. It's writing that number here is writing it in an SSD file on SSD. This number here is being written here. This number here is also being written. So now we have 4 files with these 4 numbers. And remember, we're doing a count. We're doing a count to see how many rows are in this file. In order to do that, we just need to sum up these 4 numbers. So that's basically what we're doing. These 4 records are going to be read by the next stage. So if I go back to my job and then I go to the next stage, like stage 15, let's go into stage 15 and just scroll all the way down. There's only one task here. This one task in stage 15 is reading 4 records, those 4 records from before, those 4 files from the earlier stage. And it's reading a total of 168 bytes of data. That's just 42 bytes times 4. Okay, so this stage has one task, task ID 21, and it just basically reads these 4 records and it sums up those 4 numbers, and then it gives me the results of the sum here, which is 7.2 million. Okay, let me explain this in one other dimension. We looked at all of this already. We looked at this as well. This is kind of what's going on. We have the file on S3, 255 megabytes. 4 tasks are launching. And this is how much data each one is reading. How many slots were in your cluster? Do you guys remember? 3 now, but we're running 4 tasks. Let me show you something. Let me go back here. I'm going to go to jobs, and I'm going to go into job 14 again. Specifically, I'm going to go into the first stage, stage 14, that had 4 tasks. I'm going to go into that stage. And now I'm going to show you something pretty cool. Stage 14 here, you know, that has 4 tasks, the first 4 tasks that were run. And look, they were run for like 18 seconds, 18 seconds, 17 seconds, and then 14 seconds, right? Let me show you something. If I expand event timeline here, how many people have looked at the event timeline? Raise your hand if you have. A bunch of people, about 10 people or so, out of about 60. Okay, if I expand this, look at what this shows me. This is showing me that 3 tasks ran together first, and then when this task down here, which was the last task that was run, when this task finished running, then I launched my 4th task. Do you understand what this means? This basically is telling me that I ran 4 tasks, and then, and these 3 tasks ran in parallel because I had 3 slots in my local mode cluster, so I could run 3 tasks in parallel, but then I had to run this task by itself. And the other 2 slots remained empty. And only then, after this task ran by itself, after this entire stage ran, then I ran the next stage. So this is maybe not the most optimal thing, right? There is no way to force Spark to do this work with just 3 tasks. When you're reading a CSV file, the input split for Spark to read from S3 is 64 megabytes. So it's just going to read your CSV file in 64 megabyte chunks. There's nothing you can do about that. So we're going to actually fix this performance issue by basically taking our data frame. We're going to repartition it into 3 partitions, then write it down as a Parquet file now that it's only 3 partitions. And then in the next notebook, we'll actually read that Parquet file before we actually do our sophisticated data analysis. All right, so that way, the first stage will only have 3 tasks, each task reading a third of that Parquet data. Okay. Okay, so let's go ahead and go back to the notebook. Okay, so we kind of looked at all of this, so let's just kind of skim through to this part. This is what's actually going on behind the scenes. We run our job that kicks off 2 stages. The first stage has 4 tasks. Each task reads about 1.8 million records, except the last one reads 1.6. That just is mentioning how many lines in the file we're reading. Each task emits 1 record to the local SSD. So 4 files now are on that local SSD in our local mode cluster. We have 4 files. Those 4 files are being read by the next stage, 1 task. That 1 task is not doing any remote network read. It's just reading it from the local SSD, basically, reading 4 files. So what's happening here is this 1.8 million number is the record we're writing down. This 1.6 million is just being counted and then written down. So then we have to do a global count, like a global aggregation. All right, so that's essentially what's happening here. Okay. Next, let's do a transformation order by. So we're going to take the Pageviews data frame, order it by timestamp, and then do show 10. Remember the data was out of order before? Let's see if this fixes it. This is probably going to take about 35 seconds because, and look, you can see that it's running only 3 tasks first, and then after these 3 finish, it'll probably say 1 task running. See, now it's running the last task. Okay, we should get the results in just a second. A little bit better there. I see March 16th midnight has 2 rows, desktop and mobile. 1 second after midnight, desktop and mobile. I can see in general by eyeballing, it appears desktop is receiving about twice as much traffic than mobile. Desktop, mobile. Well, look at this. Now we're seeing mobile and desktop. So usually it's showing me desktop, mobile, but here it's showing me mobile, desktop. I actually want to do a second order by to always sort the second column by mobile, then desktop. Right? So that's why this way I don't want it to show desktop, mobile, and then down here it shows mobile, desktop, right? So let's fix that as well. Let's do an order by timestamp and then an order by the site column in descending order, so it shows me mobile, then desktop. Okay, so that's what this is going to show in just a second. And after that, we'll get into reading from disk versus memory. Okay, it's almost done. It's probably, there we go. Okay, see now it's showing mobile desktop, mobile desktop, mobile desktop, mobile desktop, mobile desktop. Perfect. Okay, but that took 32 seconds to run. Each time you run any action on the data frame, it's actually reading the entire file from S3, remotely or the network. So this count operation is going to take like 30 seconds because of the read or the network. So what we should do instead is we want to cache our table. So let's take the page views by second table and call cache table operation on it. Before I do this, I want to go to the UI, click on storage up here, and notice nothing is showing up. The storage tab here only shows you what's been cached in the Spark cluster's memory. Okay, count took 30 seconds. Let me go and cache the table. Caching is a lazy operation. So if I do that and go back here, nothing shows up. I have to materialize the cache by doing an action that requires me to actually read through the data. Notice up here, a simple count took 29 seconds. This time, the count will take longer because it has to not only do the scan on disk and the count, but it has to now also cache the data in memory. So this count is a little bit unique, and it's going to take a little bit longer. So let's see how long this takes. It's probably going to take about, this one up here took 30 seconds. That one down there is probably going to take like 35 or 40 seconds. And as soon as this count is done, I should get the data showing up in my storage UI, the storage user interface. Okay, so this is running. Okay, it took 8 seconds longer because it has to also materialize the cache. And now if I come here, there's my data frame. It's an in-memory table called Pageviews by second. It's made of 4 partitions, 100% of which is in memory. And the size in memory is 192 megabytes. So it was 250 megabytes or so on disk. Why is it less in memory? Well, this is because the data is currently stored in memory in the tungsten binary format, which is a columnar compressed format that is a custom implementation of memory compression. It's actually using an encoder to do this. I'm going to get more into tungsten binary format later. The most important thing I want you to know right now is that this is incorrect. See the storage level here? The data is not deserialized in memory. Okay? What this should really say is memory tungsten binary format 1x replicated. That would be more accurate, because if you were actually like using RDDs, how many people here have done anything with RDDs? Probably everyone, right? So with RDDs, you probably know you can cache an RDD in memory. You can persist it in serialized format or deserialized format, right? You can put an RDD in memory serialized or deserialized. So you might look at this and you might think, oh, well, the data is currently deserialized in memory. That's not accurate. Don't think of it like that. A better way to think about it is, since we're using DataFrames and Spark SQL right now, since we basically ran SQL context cache table, this data is currently in tungsten binary format, and that means that we're doing columnar compression on this data. It's stored in memory using an encoder. It's not serialized or deserialized. These are not Java objects in memory. Okay? This is something different that I'm going to explain in more depth later. All you should know is that this is a little bit inaccurate. It should say tungsten binary format. If I go deeper though, under the covers, tungsten binary format does use RDDs. So I see the block name is showing up as RDDs. And I can see the last block is 44 megs and the rest are 49 megs. Okay? Just kind of keep that in mind. I'm going to explain this more in depth later. Yes?
I'm just going to ask you, on the title of the table says RDBs, is that kind of just outdated as well?
I mean, it's a little bit outdated. Under the covers, remember I was showing you in the very first notebook that basically in the primer notebook, I was telling you you should always use the higher level libraries like DataFrames and SQL, because under the covers they use the RDD API. That's what you're seeing right now. You're seeing that the DataFrame or SQL API is under the covers using RDD. Okay? But like I said, you should in 2016 don't use the RDD API directly. That's like trying to write assembly language code. That's going to be a lot harder to do. And it's much harder to get the same performance with RDD that you can get with DataFrames and SQL. Almost always DataFrame and SQL and the dataset API will give you better performance. I'm going to prove that point to you in the next hour. Actually, in the next couple of hours. I don't know if I'll get to it before lunch. Okay, let me go back to recent and go back to my notebook.
I have a quick question.
Yeah.
So in these more abstracted ways of interacting, do they all use tungsten?
If you're using DataFrames or Spark SQL or data sets, it's always using Project Tungsten's binary format in memory. And for now, all you need to know is that that's columnar compressed in memory. And it's not, Tungsten binary format does not have Java objects in memory. It uses encoders. Yeah, one more question? Why 4? Simply because in the Databricks setting, when we launched you a local mode cluster, we just set a knob to say give us a local mode cluster with 4. If you're running Spark on your own laptop, then you can decide how many cores you want in your local mode cluster. We just set it at 4. One more question? Yep. No, Parquet format is what we are using on disk right now, which is a on-disk columnar format. But in memory, Tungsten binary format is just a different in-memory representation for columnar compression. Keep in mind with page count, we're not reading from Parquet. We're reading from a CSV file right now, loaded up into memory in Tungsten binary format with 4 partitions. Yeah, the main thing is the reason I'm using like this, I'm doing cache table so that the data shows up in a pretty way here. Notice that I can read this. It says page views by second. Later on, what I'll be doing is taking a data frame and then I'll just do a .cache on it. When I do that, you'll notice that the name here will show up like a jumbled thing. Just keep that in mind. I'll show you that later. There's a reason I kind of did it like this. Just kind of hang on to that question. You'll see why I did it like this soon. Okay, I did a count. The data is in memory. How long will it take now? The count originally took about 30 seconds on disk. Now in memory, it's taking a quarter of a second. Okay, so I've gotten a, what is that, like a 50 or 100x speed up or something like that, right? Now that the data is in memory, I'm moving much faster. Okay, next. This just is showing that now every time we do something, what happened here is basically we read the data, 64 megs, and when the caching operation happened, it actually is only using 49 megs in memory to store this data. And 49 megs for this, 49 megs for this, simply because it's doing columnar compression here. Okay. Let's answer the only business question we have in this notebook. And then in the next notebook, we have a bunch of business questions we'll answer. How many rows are in the table that refer to mobile versus desktop? On the site column, let's do a filter for mobile. And remember, half the data should be mobile, right? So 7.2 million divided by half is about 3.6 million. So that's perfect. 3.6 million refers to mobile. And notice that that kicks off a Spark job as well. How many rows refer to desktop? This is easy, right? So I'm just going to show you how to do this. You can just copy this, paste it here, and this is not really a challenge. Desktop. And we should get 3.6 million there as well. 3.6 million plus 3.6 million is 7.2 million. What just happened there when I did this? I did a filter and a count, right? But what really just happened in the background? Let's look. We ran this action, this count action kicked off Spark job number 21, which had within it 2 stages. The first stage, 26, had 4 tasks. The next stage had 1 task. Now this is interesting. I added this filter, and adding this filter did not change the number of stages and tasks. So what is going on here? I still had, let me go and add this back in. And notice I'm still going to have 2 stages, first stage with 4 tasks and 1 stage with 1. So like, what happened with this filter? Where did it disappear into? Like a new user to Spark might have thought, oh, I added a filter, and maybe they'll kick off a new stage. But let me explain what's going on behind the scenes. This is like the logical model of what you might think is happening, but it's incorrect. The way you might think what's going on is we're like reading this file either from S3 or from memory. We're reading this file from memory. That's the full data. Then we're like doing a filter. And after the filter, maybe we get another data frame that has, just like the mobile data because we're doing mobile filter. And then maybe we do the count and we run some sort of count. But this is not what's really going on. This is the next diagram shows what's really going on, the physical model. What's really going on is our physical model looks very similar to when we had done just the count. We basically are reading right now from memory, actually, and not S3. 4 tasks launched. This task is reading 1.8 million records and emitting only 1 record. But what's really going on here is this 1 record only shows you the number of records, number of rows for mobile. Let me explain a little bit better. Let me zoom in on this blue rectangle. You see how there's this like 4 different blue rectangles? They're all doing the same thing in this task. There's many things happening inside this task, and those things happening are called pipelined operations. Let me show you what's happening in just this first blue rectangle. This. We have now zoomed in on just 1 task out of the 4. Inside that blue rectangle, we're reading actually from memory this time, and then we're doing a filter for keeping just out of the 1.8 million records in that first partition in memory, right? Out of here in memory, out of that first partition, which is about 50 megs with 1.8 million or so records, out of that, we're reading that, and then we're doing a filter to keep only about half of that. About 900,000 of those records are going to refer to mobile. We're doing a filter, then we're doing an aggregate. So we're actually taking the 900,000 and aggregating that into just a number, 900,000. Then we're writing that number, 900,000, into a file on SSD, which is just 1 record. It's about 42 bytes. And each of the 4 tasks is doing that. And then we have 4 different records. And then in the second stage, we just have this new task that will launch that is going to read all of those 4 files. Okay? If I can also go to jobs here, and I can go to the last job I ran, number 23, and then I can go to this first stage, 30, and expand the event timeline. And I can see now that I'm reading from memory versus reading from disk. Remember when I read from disk, we just saw green bars, right? We didn't see these colors last time when we were reading from S3. But now I see some different colors. And I can see that when this task finishes running, then I'm running this task. What are these colors? Blue is scheduler delay, and red is task deserialization time. What's basically happening is that tungsten binary format that is in memory with 4 different partitions is basically columnar compressed using an encoder. And we are basically decoding that data from memory, and that's what we're seeing in red. That is the cost of decoding that data that's columnar compressed in memory, decoding it so it's basically like uncompressed. And then in green, we're actually seeing the actual work happening. This green is the filter and the aggregate. And the shuffle right is happening so fast that I can't really even see it at the end because it's such small data. It's only 1 record, 42 bytes. If I'm troubleshooting this job right now, there's really nothing to troubleshoot. The write is happening really fast. The task deserialization time is happening fast as well. I want to point something out. The word deserialization can be confusing because you might think that's referring to like Java deserialization. That is not what that is. That's not like an RDD that is in memory that we're like deserializing. Okay, that's using encoders. So I have a slide here that I want to pull up really quick. Right here. If I had my data in an RDD in memory serialized, then RDDs get deserialized before you work on them. And that uses Java deserialization or Cairo deserialization, which is kind of slow when you're working with RDDs serialized in memory. However, tungsten binary format data, Spark uses an encoder to like uncompress it. And encoders are way faster than deserializing Java objects using Java deserialization or Cairo deserialization. So see this encoder in green? That's basically, this is just showing performance of decoders. This encoder technology is what we're seeing here in red. That is basically the decoding of the data in memory.
Does it use extra memory to deserialize there, or you have the original serialized copy plus?
That's a good question. I think we still have the original tungsten binary format data. That's basically the original data is just sitting in memory right now. It's taking up, this much data, and then when we have to work on that data, indeed, it is decoding it, and now it has in memory this second copy of the data that's decoded. So that's a good question, actually, what you just asked. Do you guys remember how big your JVM is? 3.7 gigabytes, right? Out of that 3.7 gigabyte JVM that you have right now, look, if I go to executors here, out of 3.7 gigabyte JVM, only 2.4 gigabytes is available for caching. So you see this here, 2.4 gigs. Out of that 2.4 gigs, right now, we've cached like 192 megabytes of data. But when we work on this data, we decode that 292 megs. We decode it and we put it in another part of the JVM. That's the part of the JVM that you're not seeing here. Let's see, 3.7 gigabytes minus 2.4 gigs is 1.3 gigs, right? That 1.3 gigabytes is like our working user space. So that's where we're actually decoding that data and then operating on it. And then we're done with operating on it, we just delete it from there.
So you need to account for that overhead essentially whenever
Yeah, but Spark will mostly do that automatically. But you can set this fraction manually and control that if you'd like to. At Databricks, we just kind of set it at this number. That's a good question, though. Okay, we're almost done with this lab. Next, what I want to show you is the SQL plan visualization. We can go to the SQL tab to do this. Remember, this was the last command we ran. I'll just run it again, just here. I'm going to uncomment that. I'm going to run this filter. This kicked off job 24, right? I want to learn more about what this job 24 is actually doing. So to do that, I'm going to take a look at the SQL query plan. I'm going to go to the Spark UI, and remember, I need to find job 24. So I'm going to the Spark UI. I'm going to click on the SQL tab here. Click on the SQL tab and find job 24. It might be different for you. For me, here's job 24. Don't click on that. Instead, find this, and I'm going to click on this. Okay? I just went to the SQL tab. I made sure it's the same job, and then I'm going to click on this. Okay. This is kind of showing me a visual of what's going on behind the scenes when my filter and count is running. What I'm seeing here is basically the data is being read from memory. There's a filter happening, and then there's something like a project, a tungsten aggregate, an exchange. Let me explain what this stuff is by using this diagram because I've color-coded it. So first we have the first stage. And basically, tungsten exchange means shuffle. And then we have the next stage. Every time you see tungsten exchange, it's the separator between two different stages. And shuffle here doesn't really mean any network shuffle, right? We're doing local mode cluster, only one JVM. Nothing is happening on the network. Usually, when you're running in a real cluster, the shuffle will be a little bit slower because there's network traffic happening. However, what I'm seeing here is first in-memory read. Then across all 4 tasks, we are reading across all 4 tasks 7.2 million records. And then we are projecting out. This filter gives us only 3.6 million records survive the filter. And then we project that out. Then we do a tungsten aggregate that takes those 3.6 million records and gives me 4 records out across all 4 tasks. And then those 4 records get written to local SSD. And then this next stage launches a task that reads those 4 records and emits just 1 row, because it takes those 4 numbers and it just sums them up and gives me that one number, 3.6 million. So this is what is showing me how I made basically this, right? This is how I knew this is what was going on. Okay. Also, you see this, this detail link here, details. If you expand details by clicking on it, then you'll see the logical plan, analyze logical plan. Let's do that really quick. Let me scroll down. I'm going to explain what this stuff is a little bit later, because we're going to need to maybe use this later to do some troubleshooting. For now, I just want you to notice that there's a logical plan, a parse logical plan, an analyze logical plan, optimize logical plan, and then a physical plan. Okay? This is basically showing us what's going on behind the scenes in the Catalyst Optimizer. I'm going to cover the Catalyst Optimizer in more depth later. For now, I just want to give you the Catalyst Optimizer 101. How many people here know something about Catalyst Optimizer and have maybe read about it, and this diagram they've seen before? So raise your hand if you kind of are in that ballpark. Okay, no. So let me explain what's going on. Whether you write a data frame query, like we wrote a data frame query, right? dataframe.filter.count. Whether you write a data frame query or a SQL query, as you'll see later, whether you write either one of those 2 queries, you'll always first generate a parsed logical plan. Okay? That parsed logical plan will be converted into an analyzed logical plan by doing a join to a catalog object. Then the analyzed logical plan gets converted to an optimized plan. Then several physical plans will be generated. Then a cost model check will be done to see which one is going to run the fastest. And we pick that physical plan, and then we use code generation to generate RDDs. And all the way down, we're actually running RDDs. I want to cover this in more depth later, but maybe what I'll tell you for now is this part. When we generate the parsed logical plan right now in Databricks, we basically need to take the data frame or the SQL query that people write, and currently we're using the Hive parser, the Apache Hive parser, to generate that first parsed logical plan. The way I know that is, look, if I run SQL context, it's really a Hive context. In general, you should be using the Hive context if you're running this on-prem. The Hive context will give you a richer parser. The normal Spark SQL parser is a little bit newer, so it doesn't have the richer, mature functionality of parsing like SQL queries like the Hive context does. All this is doing is it's looking at our SQL query or the data frame query and generating a parsed logical plan that looks like this. Oops. Like this. Okay, that's all you need to know right now, that this is something that is going on under the covers. I'm going to cover this more in depth later about what these different stages are along the way. Actually, I shouldn't call them stages, but steps along the way. Okay, also, by the way, if you want to learn a lot more about Catalyst's engine, then open this up in a new tab. This is a really amazing blog post written by some engineers at Databricks, Michael Armburst, Ying, Chen, Reynolds, and Matei. This blog post basically is the best place, I believe, that you can learn about the SQL Catalyst Optimizer. This literally goes behind the scenes around the math and the source code of the Catalyst Optimizer. You can actually click on these links here that say 1,000 lines of code, open that up, and you can see this step. You see right now we're at the analysis step. The analysis step takes the, I think it's the parsed logical, or the unresolved logical plan, and gives you a logical plan. Let's look at this. See, this is actually the actual code for the analyzed step. So this is the closest you can get to the source code. And in this blog post, it explains what's going on in that step. Then the next step, takes that version of the logical plan and it generates I think it's the physical plan next, and you can look at that source code as well, the optimizer. And then finally, we're running the physical plan, and you can see the code for that, and then you can see the code for code generation as well. So it's kind of beyond the scope of this course to like explain this stuff at this level of depth, but I just want to kind of leave you with this resource. And there's also a link here to the white paper for Spark SQL. Right here, this is the paper for Spark SQL that explains a lot about what's going on behind the scenes in the Catalyst optimizer. Okay, so let me just close out of all of this because this is beyond the scope of what we're going to be doing. Instead, I think we're almost done with this notebook. There's just a little bit more stuff we want to do. Recall from the first notebook that our local mode cluster has 3 slots. If we actually store the data frame in memory with 3 partitions, then it would be really ideal because the data frame would have 3 partitions and we have 3 slots, so we can analyze this data frame in parallel using 3 slots. This would be more ideal than keeping it in memory the way it is right now with 4 partitions. I could also just do like a multiple of 3, right? If this data is too large, maybe I use 6 partitions, but 4 or 5 is not very optimal. 3 is good, 6 is good, 9 is good. Those are good patterns. So I'm going to unpersist my data. I'm going to unpersist it, and now it's no longer in memory. And what I'm going to do now is I want to, basically I want to reload that data. So for this step, I'm just going to give you the code here so we can move past this quickly. What we want to do here is reread the data. So read this, you can get the answer for this from the solutions for here. Open this up in a new tab or something for 02 solutions. What we're going to do here is read the table again, order it by timestamp and site in descending order, and we're going to say cache on that. And notice what I'm doing here is a little bit different than before. I'm not like naming the table and then caching it. Here, this order by gives me back a data frame, okay? Look at this. If I take this and copy it, and then open this up in a new cell, see how this gives me back a data frame? On that data frame, I'm just calling cache. And then I'm giving it an alias here, Pageviews ordered data frame. Let's run that, and there's something I'm going to show you here. Okay, now it's like reading the data, caching it. I'm going to materialize the cache with count. Now the first thing I'm going to show you here, if you just run cache like this on a data frame, then when the cached version of the data frame shows up in memory, it's not going to have a clean name. It's going to have like that jumbled up name I was hinting towards before. Okay, so let me just give it a second. I have to wait for this count operation to kick off before this is going to show up in memory. Okay, so there's like a few points I need to make here that are kind of like intermediate level points. The first point here is that ideally don't cache data frames like this. Okay, I'm going to show you the correct strategy for how to do this in the next lab in just a bit. But I'm going to show you the problem that will happen when you do a cache like this. This count is materializing the cache right now. I have a question. How many partitions do people think are going to show up in memory right now? How many people think the data frame in memory is going to have 3 partitions? No one. That's good. How many people think there will be 4 partitions? Almost everyone. Okay. Let me go to the memory UI. See, this is the jumbled up way it shows up. If you just do dataframe.cache, it shows up like this. It's hard to know what this is. But look, 200 partitions. Each partition is tiny. 600 kilobytes or something. This is non-optimal. Ideally, you want a partition in memory to be somewhere between 50 megabytes to maybe like 200 megabytes. That's a healthy partition, somewhere between 50 megabytes to maybe 200 megabytes. So what happened here? Like notice, all I did here is this. This is all the code. I read the table, ordered it, cached it, and then I just basically took that data frame and I ran dot count on it. So let me look at what's going on here, but I need to diagnose what's going on now. So I'm going to expand the Spark jobs here. I'm going to see that that ran job 26. Let's look at job 26. So interesting. 3 stages. First, I used 4 tasks to read the data. And we understand what's happening there, right? 64 megs, 64 megs, 64 megs. Last task reads 58 megs. What happened here, though? So to understand this, by the way, I can do on the data frame, I can call RDD partition size and I'll see 200. Okay, so let me explain what's going on. There's this setting, a default setting in Spark called Spark SQL Shuffle Partitions. It's set to 200 by default. What is this setting? So the way to learn this is we want to go to the Spark documentation. So on Google, I'm just going to search Google for Spark Docs. Oops, not Google Maps. That won't work. Oh my God. Okay, let's do it that way. Search Google for Spark Docs, go to Spark Docs, and then we're going to go to Programming Guides, DataFrames. Under DataFrames, I'm going to search for that setting, Spark SQL Shuffle Partitions. So there's some setting here, it defaults to 200. This configures the number of partitions to use when shuffling data for joins or aggregations. So when it was doing that shuffle between the 4 tasks and the next stage, there's just a setting that's set to 200 by default. Now this is just a hard set number. In a future version of Spark, like Spark I think 2.1, this number is going to be dynamically set, where it's not just going to always, after a shuffle, give you a data frame with 200 partitions, but instead it's going to look at how much data there is, and it's called adaptive shuffle, that feature. It's not in Spark 1.6. Adaptive shuffle is, I think, coming in 2.0 or 2.1. But in Spark 1.6, I need to control the setting based on the number of slots I have in my cluster. I'm going to change that setting to 3 right now. Okay, now I can do this get conf now, and I can see that it's now set to 3. I did SQL context set conf to change it to 3. Then I'm going to unpersist my data frame. I'm going to run the exact same code again, okay, to read the table and to count. And now it should show me that it's going to go from 4 tasks in the first stage to 3 tasks, and then it should put the data in memory with only 3 partitions. The reason I did 3 is because I know that if I use 3 partitions, every partition will be in that sweet spot of 50 megabytes to 200 megabytes. If I had a really big data frame or a lot of data, like 50 gigabytes on disk, I'm not going to use 3. I'm going to use a different number, like maybe, I don't know, 30 or something, some multiple of 3. There's a question? Yes?
So here you basically took everything we did before but combined it on one line. So why did this do 200 and before it only had 4?
The question is, I just did everything I did before and I combined it on one line. Why did this do 200? Well, yeah, before we actually cached this table, before we did the order by or anything like that. The order by is what's triggering that shuffle to happen, that's kicking off that stage with 200. But before, what I had done is I just took this table in the very beginning and I just cached it right away. And then on that, I got a data frame, and then I did an order by later. So that basically was what was going on. If I do a count now and go back and look at storage, notice now I have a data frame with only 3 partitions in memory. Each partition is like 40 megabytes, basically. All right? And now if I expand the jobs, I can see that instead of 200 tasks, every time a shuffle happens, it's going to try to give me a data frame after a shuffle with 3 partitions. The exception here is if you do a count and it's doing this type of aggregation, it's always going to use just one task for the last stage before a count. Yes?
So it seems like kind of a happy coincidence that the partition size is roughly correct and we use all the tools. So what's more important?
It's a happy coincidence you're saying that I'm using just 3 partitions and therefore I'm using all 3 cores simultaneously. That is indeed true. All I'm saying is if you have more data, like 500 megs of data, then just use 6 as a number of partitions instead of 3, and that will work fine as well. Just use a multiple of 3. That way, if I have 4, did you notice what happened before? I was running 3 tasks, then I was running just 1 task by itself. That's why I'm saying use a multiple of 3, or use a multiple of the number of slots that you have in the cluster. Yes?
How do you determine like the optimal thing? So you mentioned like number of slots, but what happens if you have like a really large cluster?
Yeah, how do you determine this? This is kind of more of an art than a science. I mean, ideally, I want a partition to host about 50 megs to 200 megs. So that's like the math I'm going to be using. I'm just going to kind of play around with it, try some different numbers until I get that sweet spot in memory. Yes?
You can above the 20 megabyte.
How did I come about that?
Yeah.
That's just best practices in Spark.
There's no reason behind it?
There is reason behind it. The reason is because you basically don't want to use a partition size that is really large, like 2 gigs, because what might happen then when you analyze that 2 gigabyte partition, it might take, like 20 seconds to run that, okay? If it takes like 20 seconds to run that, then what might happen is sometimes at the very end of a job, the last task that's running, it might run by itself and it'll take 20 seconds. So the idea here is if one of these partitions gets lost in memory because of memory pressure, then it has to reread from disk. And when it rereads from disk to rematerialize that memory partition, it might take a really long time to just do it for that one partition to recreate it in memory. But if you have only 50 megs to 200 megabyte partitions, and even if that situation happens where you lost a partition in memory because of memory pressure and you had to reread it, it won't take too long. That's why you don't want to have really large memory partitions. You don't want to have too small ones because then just the cost of the driver sending tasks to run a little tiny job, a little tiny task, each task is taking like 2 milliseconds to run, that's going to just cause a lot of traffic in your cluster to run really tiny tasks, and the overhead now is going to be the scheduling delay of sending the task from the driver to the executors, was going to take up most of the time. Right? This is the same reason that in Hadoop MapReduce you do HDFS block size of 128 megabytes, because you ideally want in Hadoop MapReduce a task running for somewhere between 30 seconds to 1 minute in Hadoop MapReduce. The reason you do that is because you don't want a task in Hadoop running for 5 minutes, because if that's the last task that's going to run by itself, it's going to run for 5 minutes. And that's the only task that's running. Maybe everything else is just waiting. It's the same thing, but in Spark, you ideally want a task to run for somewhere between like maybe 10 milliseconds to maybe like 1 second or 2 seconds. That's the sweet spot you want each task in Spark to run for. If it's not in that sweet spot, then either increase or decrease the partition size. Okay. Yes?
If you run the count again, it still shows 3 stages, but the first one gets skipped.
Yeah, that's a good question. I ran it again and the first stage got skipped. What happened here? Great question. What's happening here is Spark has an internal optimization it's doing where, the shuffle files from before, they're still there. From the first time I ran it, those 4 files, each one with 42 bytes of data. And Spark was able to see those files from before, and it's just using those files to run this next query. Meaning this time, we actually didn't read from memory at all with this count. This count didn't run that first stage at all. It just basically read those 4 shuffle files. Does that clear? This is important to understand actually. This time the count, it's not reading from S3 or from memory. It's reading the temporary shuffle file that's still there. Spark eventually deletes those shuffle files, but it keeps it for a while until there's disk pressure on SSD. Then it'll start deleting the old shuffle files. This basically means that if you do a count multiple times, and forget the memory thing, if you just kind of are reading something from Cassandra or JDBC or S3, and then you do a count twice, the second time is not reading from S3. The second time it's just going to do this trick to read the shuffle files. Therefore, if you are doing updates to Cassandra or JDBC and you do a count twice, the second count will not pick up the data from Cassandra or JDBC because of this internal trick. The only way around this trick is you're going to have to recreate the data. So you'd have to rerun this and give this a new name, like 2. Then it'll trigger to actually reread it all the way. Okay. We're almost done with this notebook. Yeah, actually, I guess we are done with this notebook. So this was a kind of complicated notebook. We went kind of behind the scenes in a lot of stuff. Are there any other questions before I set the stage for the next notebook? Yes. You have to set it, I believe, for every notebook right now.
Would you be able to do something like figure out the size of the thing and then figure out how many slots you have and do some division on the fly and then do it? Because I think the other thing is you have like a data set and that can evolve over time, right?
Sure.
After 2 or 3 months.
I mean, the easy answer to that is just wait for Spark, I think it's 2.0 or 2.1 that has adaptive shuffle, and then it'll automatically decide that number intelligently for you. Right now, you have to set it manually in the beginning of every notebook to have it do it correctly. And yeah, I guess if your data set is changing in time, then you'll need to change that after a few months to a larger number. We only have about 7 minutes before lunch, so what I would like to do right now is actually just jump into the next notebook, and I would like to just kind of do the beginning part of the next notebook just to get it set correctly. Okay, so let's do this. Let's go into the 03 notebook, open that up, close your Spark UI, close out tabs you don't need, attach it to your cluster and restart your cluster. Okay, so attach it to your cluster, restart your cluster, and then in this notebook, we're going to keep looking at the same data set, but after this notebook, we'll actually jump into different data sets like Clickstream or actual English Wikipedia. But in this one, what we're going to do is, now that we just did a whole bunch of data engineering, we're going to do data analyst work. So we're going to actually answer some questions and do some queries. It looks like my cluster is still restarting. Take a second to skim through the questions we're going to answer right now. We're not going to do most of this work. We're just going to set the stage, and I'm going to just introduce this notebook. Then when we come back from lunch, we'll actually do some of this stuff. Here are the technical things we're going to be doing right now. So we'll make a UDF, we'll do a Matplotlib visualization, and this notebook actually has a pretty interesting challenge exercise as well that will be interesting to see if you guys can figure out. Okay, so look at what we're doing here. We're basically, the data analyst is implementing the best practices from the data engineer. So we're going to go ahead and set this number to 3 for Spark SQL shuffle partitions. And then we are reading the table, ordering it. And then look at what we're doing right now. I don't have a cache at the end here. You guys notice that? I basically set this setting, and then I'm reading my table page views by second, ordering it by timestamp. Then you get Pageviews data frame. No such table exception. Hang on just a second. What we need to do is go back and find that cell in the second notebook that we used to read the data from S3. So let's go to the second notebook. And here when we first read the data, let's copy that cell. Not this part, but right here. See this part? When we did the page views create data frame, let's go and copy this. So I went to the 02 Data Analyst notebook, and I just scroll down like the top 10% of the notebook, find this one, PV loader data frame, copy that, okay? Then go back to the 03 notebook. And then here, open up a new cell above this one and just paste the code in. And then let's run this cell. And then now this notebook has access to page views by second table. And then let's run this command to read the table and order it. Notice I'm not doing a cache right now. The reason is because I want to show you how you can take a data frame and put it in memory with a clean name, with a name that's readable and not jumbled up. So everybody should just run this, and now we have access to this table, page views by second. Now run this cell again. There we go. It sees a data frame now for page views data frame. And then look what I'm doing here. On page views data frame, which basically has the data ordered by timestamp and site, on page views data frame, I'm doing this, register temp table, call it page views by second ordered, and then do SQL context cache table, page views by second ordered. Let's run that. This is how you give it a clean name, by registering a temp table with a unique name, and then doing a SQL context cache table on that table name. And then just do a count to materialize the cache. And then when the count is done, I should see it in memory. And it should have just 3 partitions. Okay, so I'll go and open up the UI again. Since I restarted the cluster, the UI will be new now, so I have to reopen it. Go to storage, and it's not in memory yet. It's probably still doing the count operation. There we go, now it's running. Okay, almost done. So I used 4 tasks to read the file fundamentally from S3. Then it did a shuffle and made 3 tasks. Okay, there we go, it's done. Storage UI, there we go. It has a clean name, page views by second ordered, 3 partitions. It's in tungsten binary format in memory. And there we go, everything was good. Another important thing I usually like to do is I like to make sure that each partition is roughly the equal size. Yeah, there we go. I don't have a lopsided partition where one of them is 2 gigs and everything else is, 2 megabytes. So this looks healthy. And another thing I might do really quickly is just do a show 6. The data looks good. It's in order. And I can do a count to just see how long this will take to run in memory, 1/4 of a second. Okay, it's exactly noon. We'll take a break for 1 hour for lunch. We'll come back exactly at 1 p.m. When we come back, your cluster will probably have self-terminated. So what we'll do is we'll just rerun the first 10 cells in this notebook. We'll just hit Shift-Enter until we get back to this count, and then we'll resume from there. I would like to ask everyone to actually just take your laptop with you. We're not going to have like somebody, you can leave your power cord here, but take your laptop with you. And try to be back by like 12:45 if you can, because I'm going to resume exactly at 1 p.m. because we have just a lot of stuff I want to try to cover. So yeah, we'll resume exactly at 1 p.m. and then we'll just kind of keep continuing.